2018 and heads the product development, works with owners, developers, and EPCs deploying PV in 4 continents. Just for his background, Pedro is really one of the pioneers in trackers. He's been working in that field from the early days when trackers were utilized in Spain in the first feed-in tariff wave, and he has been working for several companies, and I'm very glad to have Pedro share today with us about large size modules and the trackers of Arctech Solar. Pedro, the floor is yours.
Thank you, Michael. So I'm about to share my screen right now. I will try to gain us a few minutes here so we recover some time there. So I will touch upon some points that Kevin has mentioned in his presentation. My main goal is not just to present everything that Arctech does or offers to our customers. Instead, I'm going to be focusing specifically in what today we consider the single most important issue or topic, if you will, with regards to trackers, and that is stability in the field and how trackers transitioned from a shorter size panel, a 2x1 panel, from to 2.4 by 1.3 in some cases. Okay, this is the only slide that I will talk about Arctech's product line, and then I'll be more specific. But like I typically tell everybody, we've been the top 5 tracker manufacturers in the world, and we are probably the only one with the gigawatt deployment rate on both 1P and 2P architectures. Those are the most popular architectures. So we are not, your tracker guy that's gonna just say that 2P is awesome and 1P sucks and vice versa, because we both understand really well the advantages and disadvantages on a per project basis of these 2 architectures. Okay. Regardless architecture, there are five traits that are common in our trackers. We only have independent, or we only deploy independent rows. We are not believers of ganked solutions, not even a dual row. We can adapt grade to slopes up to 20% there. And very importantly, we power our trackers from the string directly. We are not believers either of dedicated panels and cycling batteries from 0 to 100 and 100 to 0 every day, because those batteries will not last in the field. And we think that our customers do not appreciate changing batteries very frequently. And then we have all those routines about the artificial intelligence. Kevin touched upon that. Well, I think everybody has something similar at this point with topographic and partial shading and all that stuff. So that's not the focus of my presentation. The focus of my presentation is to understand what happened to trackers as modules grew in size. Okay, so this is a chart that shows that trend. I checked the attendees list, and there's a lot of known faces already. I apologize in advance if you heard this speech from me more than one time, but hopefully it's going to be useful for some other people. But anyways, back to the point. Modules used to be 2x1. This is a length distribution chart. So all major manufacturers used to have their length in 2 meters. Everybody pushed the boundaries. We are now at 2.2, 2.3, 2.4. Same thing happened with width. No more 1 meter width. Now we are at 1.1 or 1.3, as we all know. So what happens to trackers? Well, one good way to illustrate that is like a real project, 100 and something megawatt project we did in Australia, and everything was designed in with the typical 2x1 400 watt tracker. And then all of a sudden the guys come and they say, oh, we have a much more powerful module that lowers our LCOE, that improves our finances, so we need to design this thing in right away. And we were used that when panels used to grow in size, the voltage, the open circuit voltage, would also go up, and we would reduce the number of panels per string. Now that's not happening anymore, because see, power is much higher, but VOC is the same. What does that mean? That means that we have the same number of panels per string, but larger panels. So trackers grow both in length and chord. Now they are longer and taller, okay? What does that entail? Well, if you did all your wind tunnel studies for the previous size, your tracker, your old tracker, is not valid anymore for the new panels. I'm very sorry. So you need just to go do that all again, okay? And if you don't do anything, that means, and you keep your tracker, that the performance of your tracker is getting lower performance, mainly in terms of stability, right? So if you take anything from this presentation, one of the take-homes or takeaways is the following. You used to have a tracker with the old panel. The module changed, the panel changed. If you did not change your tracker, one or two things: your tracker is not valid anymore, or your performance went from here to here, right? Let's see how that affected the tracker. So, you know, I'm going to divide these effects into two different categories. One thing is how it affects the resistance of the tracker. That means, you know, the way you size components, and the other way, but probably the most important one, is the stability of the tracker. Okay, so in terms of resistance, this is a real exercise that we have done. You know, about 1 year ago, when the first trackers increased their length from 2 meters to 2.3, that module length translates into tracker chord. And here we go. Torsional moment increases from 5 to 10% in a range of 4 to 10%. Same thing with normal force. You know, surface is much larger, and not only the static loads but also the dynamic loads. The dynamic amplification factors also grow from 4 to 9%. The bad thing is that all of these three things are cumulative. So you may be looking at the tracker that is seeing up to, you know, 25% more load just by using the new panels. Okay, so you need to bear that in mind. On the other side, in stability, you know, everybody talks about they're elastic, and there seems to be a big buzzword. So if you don't understand what that is, well, that's what it is. You know, this is an elastic test video clip. It's basically putting real trackers with the same stiffness, the same damping ratio, the same natural frequency that you have out in the field into the tunnel, and see how they react when the wind comes. All right, and we are particularly interested in three different modes. Everybody talks about fluttering and stability and torsional galloping, and, you know, throws all these big words. A lot of people don't even know what that means, but you know, it all boils down to these three modes. Okay, trackers, as Kevin was saying before, are, or used to be, somewhat flexible structures. They move. These three modes here are their trackers' main modes. Okay, so now what happens? A traditional tracker, as I like to call it, which is a tracker, you know, the type of trackers that has been deployed so far, used to have like you know, one fixed point in the center, and then a very long half wing. I'm going to call this half wing a fixed to free span. Okay, very long fixed to free span. And since this fixed to free span is so long, the tracker moves a lot, as you can see in this little animation here, when the wind comes. Okay, this is called a traditional flexible tracker. These trackers used to work pretty good. Well, if you do the things right, by the way, with the 2x1 panels. But as I explained before, if you increase chord, if you increase length, you have a big challenge. Take a look at these two curves. These are real stability maps of our trackers, 2P and 1P, right? That we obtain after all our wind tunnel testing. And you can see here a common trait. The worst tilt to put your tracker at when the wind comes is 0 degrees. You can see the lowest value of critical wind speed sits at 0 in both cases. For the ones who do not know what critical wind speed means, that's the wind speed upon which the tracker just starts moving too much. Okay, this critical wind speed is function of rigidity around 0 degrees and damping ratio at steep angles. Save this note because it's going to be useful for later. But the point I wanted to make is, if you have a traditional flexible tracker, like most people used to have, and you are stowing that tracker at 0 degrees, you are likely to be seeing incidents like this, which are no fun. Let me tell you that right now. Okay? So again, do you have a traditional flexible tracker? Run away from 0 degrees, please. And from everybody else that claims that 0 degrees is a good stow position. Okay? So you need to stow your tracker away from 0 at the steep angle if you want to protect your tracker in your installation. Okay? Now, what is the problem when the tracker increases size because the modules now are larger as well? Well, you are protecting the tracker by stowing the tracker at the steep angle, but you are not getting rid of the performance at 0 degrees. That performance is still there. So if you're 0 degrees because the tracker is longer, because the tracker is wider, is your worst position, now it got even worse. So your operational wind speed, I'm not talking about survivability anymore, I'm talking about the operational wind speed comes down with the new modules, okay? So that may be a problem for your developer or your customer, because they used to stow, I don't know, the tracker at 18 meters per second, 20 meters per second. Now they have to stow at 15 or even 10. That means that they will be losing a lot of generation. Not ideal, okay? Anyways, quick summary here. We used to have 2x1 modules, 400 watt modules. Trackers used to be, I have my picture right here in front, around 60 meters if you put like 4 strings. Now with the Vertex that Kevin was just talking about, they go up to 90 meters. What are you going to do? You're going to cope without all that performance lost? You're going to redo the whole thing? Well, probably need to think about it, right? I'll tell you what we have done. But the challenges are, with those modules, we have higher loads. So your components would need to use more steel. And your stability comes down. And that poses 2 challenges. One, you need to make the tracker more rigid, which is more steel again, and you need to compromise your energy generation, okay? Because of that, because your curve, the whole curve shifts down, okay? Good. Now, before we go to the solutions, because this is not only talking problems here or challenges, I'd like to provide some solutions too. But before we go there, let me talk about the interaction between, what I like to call the tracker and module paradox. If you have a traditional flexible tracker again, like I was talking, you must stow the tracker at the steeper tilt, okay? In my example here, this tracker is stowed at 0 degrees, and it's the only way for the tracker not to fly away. If it is a traditional flexible tracker, typically with a single point in the center, okay? Now, the thing is that the pressure profile on top of that surface on those panels is much higher. You can see some numbers here. It's about double sometimes. So it's pretty bad for the panels, by the way. What would be great for the panels is if the tracker is at 0. But we cannot put the tracker at 0 because everything flies away. So, this is the paradox, right? We either protect the tracker in the whole installation, and then the wind comes, and okay, at least, it still exists. Or if we try to protect the panels, then everything goes. So, what is good for the tracker is not good for the panels. And by the way, these new panels, instead of 2x1 being 2.4 by 1.3, have 58% more surface. So they suffer this pressure way more. Everybody thinks about those 2400 Pascal in the IEC and the load and the pressure test. Forget about that with these large panels. You are stowing your tracker at 45, at 50 degrees, not compliant. I'm sorry, you are not, because your surface increased like a lot. Okay, so you need to do something else. You need to be able to safely stow at 0 without the tracker flying away. How do you do that? That's what I'm about to show. These are some more charts about the effect on panels. I think you got that. You know, the thing is, when you are stowing this tracker right there, and now you have a larger panel size, you go way beyond the 2400 Pascal, like I'm saying. And although you do not see you know, visible damage when the storm goes away, look what happens to your cells. All delaminated and micro cracked. But not all of them. You know, it's better than trackers flying away for sure, because you used to have an asset, and now you don't have an asset no more if the trackers fly away. But when the storm comes, you are looking at your SCADA, and your SCADA says, oh, you know what? This string is underperforming. That string is only at 20%. That string is at 30%. Why? Because you have lots of micro cracks, or you have delamination in your cells. And that's because you're stowing the panels like that and the pressure is too large. So no good for the panels. So I claim here before you all, 200 people something listening to me at this point. With a new panel size, stowing the trackers at a steep angle is not the solution. Yes, it's better than trackers flying away, but it's not a full 100% compliant solution, because you're hurting your panels. You're hurting the asset of your customer. That's what you're doing. So what are we supposed to do? Let me speed up a little bit here. We'll talk about this, blah, 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 blah. So we need to go from a traditional tracker that is very flexible to a rigid tracker. If the tracker is rigid, okay, it can stow at 0 because it doesn't go anymore. It doesn't have too much deflection, so it diverges, okay? And this is what we have been doing since late summer last year when we launched our first rigid tracker. We started by 2P because these excessive deflection phenomena, you know, are more pronounced in 2P trackers. And we launched our SkySmart 2. You know, what you can see here is a configuration with 3 fixed points. These are the same same type of slew drives we used to have before. But we have done projects with 3, with 4, and even with 5 slew drives, right? So one note for you all. The key thing here is not, oh, you know, I go from one single drive to many single drives. Yes, that is necessary. But if you're procuring trackers, what you really want to ask about is the distance between those fixed to fixed points and the fixed to free points. Okay, it's not only necessary to have more fixed points, it's necessary to control the distance among those fixed points and the fixed to free. That is the key for your stability. So don't get fooled with somebody that says, oh, now my tracker has 2 fixed points. Well, but the tracker is 150 meters long. That doesn't matter, because in between those fixed points, you still have 100 meters. You divide that by 2, you still have the same 50 meters as the tracker up here. So you accomplished a bunch of nothing, okay? So the key here is control the distances between your fixed to fixed. The distance that you care about is L divided by 2, and your fixed to free, and the distance you care about is L. Take a look at this tracker right there. Let me see if you can. Yes, I can do that. The distance from here to here in a typical 1P 1P tracker used to be, I don't know, 45 to 50 meters, okay? That distance translates in the new system right there into this distance right there. So if my distance here is 10 meters, that means that I am 5 times more stable in this chunk right there. This is what you need to ask for. Same thing here. If my distance from here to here is now, I don't know, 25 meters or 20 meters, the L that you care about is this divided by 2, which is the same 10 meters. So this tracker as a whole is 5 times more stable. Do you understand the physics here? This is what's really important, okay? Not only, oh, I put more than one. No, I know what to do with my geometry. Anyways, a few examples for you. Oh, this doesn't move no more. Oh, there we go. Okay, so 2 videos. Above, you can see a flexible tracker. Look at how these guys are moving. You know what's interesting? You have flexible trackers in the field. The first row, boom, goes to a very steep angle and stays right there. This row is often not a problem, but you are listening to these people saying, oh, exterior rows, exterior rows. Well, yeah, exterior rows, but the exterior rows are not the ones failing by divergence, by torsional stability. Look at those rows out there. You know, these ones need, slight larger components, but these are not the ones going crazy. Behind here, below, sorry, not behind. You have a fixed tracker. We have several fixed points here in those posts. You cannot see probably very well, but this is a fixed tracker. This wind speed right here is double this wind speed right there, and the whole behavior is very predictable. So I know exactly how much wind speed the whole plant can take. This one is very erratic, very difficult to control. If you really want to do a good job, we should be looking at these guys right there, not much the first and the second row. Okay, so take a look at the instability curve of a fixed to fixed, of a rigid tracker and a flexible tracker. This one you know already. This is a flexible tracker with very long fixed to free span. Okay, what's the worst position again? 0. Stay away from 0 if you have this tracker. Take a look at this curve right there. It's the opposite. With a rigid tracker, all of a sudden, we realize that the best position is 0. So it's not that it's nice to stow at 0, it's that you must stow at 0. Okay? The highest critical wind speed is at 0. And why is that? Because this tracker does not move. It's very rigid. The distance between rigid points is very short. All right? So I have some values for you of critical wind speed. And, if you have a tracker like there in the top, you must stow at steep tilts. And, you can do projects in these wind speeds, or for these wind speeds, these are the maximum wind speeds. You can see that 2P struggles a little bit more than 1P if your tracker is flexible. That's not news. But if you go to a rigid tracker and you are stowing at 0, take a look at the significant improvements. 2 improvements. First, you're being panel friendly. And second, your tracker performance is increasing, not decreasing. Okay? If you compare the worst spots, well, here the worst spot is around 20 meters per second. Here the worst spot is like 35, 40 meters per second. Very far away from one wind stow. So the key here is that, do you have large panels, very large panels, 2.4, 1.3? I don't think your traditional flexible tracker cuts it anymore. Do you have a tracker whose distance from the fixed point to the end is like 20 meters, 23 meters? I don't think so. It's not going to work that well. Ask for that distance. Ask for those critical wind speeds. Those distances need to be reduced if you want a rigid tracker that can safely stow at 0. Okay? And that's what we have done at Arctech. We have an evolution in our product line, and we have like our SkySmart 2 and our Skyline 2. Both 1P and 2P, but with many fixed points along the torque tube. Take a look. And the good thing is that it's very modular. This would be, for instance, the Skyline 2 with 1 string only, 2 slew drives. Do I care about how many slew drives? No. The only thing I care about is the distance between the fixed to fixed and the fixed to free. This is like 20 meters. This is 10 meters tops. So you don't have very long spans. That's what I'm saying. And by doing this thing modular, I can pack as many fixed to fixed points as I want and do it a 1 string tracker, 2 string tracker, 3 string tracker. So different overall lengths, but with the same stability. That's what's, you know, a benefit, that one of the major benefits of this design. Okay, same thing with SkySmart 2. I mentioned, you know, 3, 4, 5 fixed points. Again, compatible, truly compatible with all panels. Why? Because we put more or less span length. Okay, well, I guess I'm repeating myself. I think you guys got the idea. Last slide, just to summarize everything I said. So if I have many fixed points, that allows me for shorter spans, and this is the key. Ask for your span length. I cannot repeat myself enough. If your spans are short, your structure is stiff. If your structure is stiff, it doesn't deflect. And if it doesn't deflect, the wind speed goes up. You are safe in very high wind speeds, okay? And that allows you for safely stowing a tracker at 0 degrees for the first time. Flexible trackers don't stow at 0, okay? Rigid trackers, you should stow at 0, but you gotta make sure that you have a rigid tracker. And sometimes just putting many slew drives or many actuators or whatever is not a rigid tracker. Go check your spans again. Well, if you can get a rigid tracker, you stow that tracker at 0, your panels see less pressure. And if they see less pressure, you are not hurting your panels. You are staying within acceptable pressure values or magnitudes. So your cells are not delaminated, okay? Your cells are not cracking. That means that your asset is more protected.
Thank you. Thank you, Pedro. That was a great presentation. A lot of great comments. You'll see that. Please answer questions in the Q&A. We got to run. Next.